Okay, today what I want to do is talk about what it means to be developing cross-platform applications, and I really want to go through a little bit of the history of how did we even get here? Why are we writing in C Sharp? I mean, what's the benefit of that? Um, and I also want to talk about how cross-platform mobile development has been evolving over, the last few years. So I'm going to start out just by how did we even get here? I mean, why are we picking the language that we're picking? I mean, obviously I'm telling you, you got to write C Sharp. You'll get a job if you write C Sharp. But why? Why C Sharp? Why are we here? And there's other languages, but just in our area. Um, so if we start way at the bottom, the lowest level is the machine language, and that's all ones and zeros. And if you think about where programming really started, with like card readers, and I'm not talking about digital chip card readers. I'm talking about the actual punch cards that people would have to like run stacks of paper cards with holes through machines, and it had pins, and if the pin slid through the hole, that's a 1. If it didn't slide through the hole, it was blocked because there's no hole punched, that's a 0. So they would be on and off. We're really doing the same thing today, it's just different. So once it's compiled down to the lowest possible level, we're down to that machine language, and that's all ones and zeros. That's all the opcodes inside our CPUs truly understand. It's just routing our bits the way that we need to route them to get the results that we're looking for. So that's machine language. Then a higher level language came, which was assembler, and now we're dealing with even higher level languages. So like C++. And then we get into Java, and we get into C Sharp. So it's been evolving. So I oversimplified this slide a little bit, the machine language, just to keep it simple. Maybe I have like a 3, which represents multiplication. I've got a 6, and I've got an 8. Now, that really would be in binary, and those would be longer numbers. But the CPU would get the first, set of numbers, which would be, okay, you need to multiply, and then this is the value, and then this is the other value, and then the CPU would actually multiply those values and return the result. Assembler became a little bit easier. Instead of having to specifically know the bytes, we got a little bit better human readable, like mult, and even once we get into like C++, it gets even better. But the problem that we deal with all of the lower level languages, including C and C++, is those programs are being programmed specifically to specific hardware, CPU, and also operating systems, and dealing with different constraints. So I can't just take a program for Windows and drop it on a Linux machine, double click on it, and run it. It won't work that way. So back in the day, it was really, really bad. There were tons of different CPUs. And today, in the electronics world, it's still that way. It's still bad. I mean, there's tons of different microcontrollers and microprocessors, and people have to write code specific to that chipset. And it used to be that way with CPUs. I mean, I think we were getting somewhat of a standardized set of instructions, but they still kind of go between different processors with different subsets. But there's still tons of people out there that write code. They have to use a systems reference guide, and I couldn't imagine having to be a programmer like that. But you want to figure out how to maybe subtract a couple numbers, you got to pull the guide out and look it up and say, okay, well, I want to subtract, and I want to do a specific normalized subtraction, so, okay, well, that's going to be my operation code for that. My op code is going to be 2b, so that's going to be what I'm going to type into the source code, so that way this specific processor will be able to subtract. The problem is 2b may be subtraction for, in this case, the 370, but maybe the 480, will be a different opcode. So it's specific to the hardware. And that becomes really tough. You get a different chip. You got to go in through all your source code, change all your opcodes to support the new chipset. Okay, so it became a mess really quick, and it really became difficult to port applications from one chipset to another, and it's still difficult. I mean, a lot of people for hobbies take like Doom, the old 1990, I think, somewhere around there, video game that was written in C++, which is even a higher level language, but it's still trying to port that to a different operating system. So people will take it and just to learn, because it was written for the Windows operating system, rework all of the code to make it work on Linux or make it work on a Mac. So that's just one of the things. It's just still, you can't just move things around today. So back then, they were very machine specific. So this is the code, and it's still like that with microcontrollers. If I want to do something for an Atmel, I need to look up their code. I need to use their compiler, all right, because their compiler is going to do all of that even in C++. You have to get the compiler for that specific chip. And even if I abstract some of the code, because it's gotten better, I mean, C++, we now have things like an integer, and 6 times 7, all right, so this would be C++. Well, that works great for a specific chip, but if I want to run it on a different chip, I actually have to recompile it. And sometimes chips don't have all of the features, so then the compiler will break, and then you'll have to clean up your code. So it helped. It's definitely a lot better than low-level details. We don't want to be looking up opcodes. If I want to multiply, I use a multiplication operator, and that's nice. So it has gotten better, but still, portability is not nearly as nice as it could be. So we still have APIs. We still have like the Win32, Mac, Linux. We've got all the different operating-specific constraints we have to think about when we write code. So what happened is in the early days, Sun came out with this whole idea that we would create a Java virtual machine, the JVM. And what they thought is instead of like using the actual CPU, we'll make source code to go against a virtual CPU. So that way we know what it is. And then we will map that virtual CPU to the real CPU, and then programmers could just write code and it will work across the board. So basically the virtual machine would do all of the translation to the native CPU. So the way this worked is I would write virtual machine code. Now in this case, virtual machine code would be Java. It would also be C#. So it's more a language that is intended to work on a virtual machine of some fashion. So the virtual machine would be the thing that would be interpreting it, and then it would then create native code, and then that native code would execute on the native CPU. And I know this seems like, wow, why would you really do that? But the thing is this virtual machine, Java has the JVM, .NET has the .NET framework, and what that means is I can write my code, and that same code will run the same if it's on a Linux machine or if it's on a Windows machine or a Mac. So what's actually happening is this JVM, the Java Virtual Machine, is going to be mapped to the CPU itself. My code no longer has to be affected by the operating system or the chipset. The machine itself that somebody else wrote has all of that mapping already in place for me. So the good thing is 100% portability. I write an application, I write my code, and it is going to work everywhere. It's going to work everywhere where there's a virtual machine made for it. So I have to have a virtual machine that has been made for the specific operating system. If that exists, then life is good. I can write it once, I can share it, and VMs are completely different machines. So every operating system would have its own VM. No extra effort for portability. So I don't have to tweak any of my code. Nothing changes. So it's actually a good thing. So So I'm gonna pick on Sun here a little bit. I'm gonna pick on Java. All right. So what happened is Java created a virtual machine for Windows. They also created that virtual machine for Linux and Mac and many other operating systems. I mean, there's a lot of it. So if I were a Java developer, and back in the 90s this was huge, this exploded because I write my program and I give out my jar or whatever the application is that the user is going to run. They just download it. I put it on my website and say, here's the app, download it. They download it, and if they're a Windows user, they may have to install the JVM, which I'm sure some of you all have done. When you double click on it, that JVM is going to run the program in there, and then because Java did all of the mapping for us between Windows and the Windows operating system and the chipset, it can then execute that code. So me as a programmer, I don't care. I just write my code, compile it, distribute it, and life is good. And the same thing is going on with C#. So now we're using something called the .NET Framework, and the process is actually called JITting. It's just-in-time compilation, and that's what's going on at that point. So that's a little bit about the higher levels. So what's the problem? So the overhead. You know, I mean, you want to run something. You're not down to the metal like C++. Most games today are still written in C++, sometimes even lower level, because they're trying to get down to the metal as much as they can, which means they don't have to do any interpolating or any type of thing going on. So my code runs in a virtual processor. Then that virtual processor rearranges the code so that way it'll work on a real processor. That takes time. All right, so that's really the overhead. So what's going on with C#? You know, so Microsoft does what Microsoft does really well. During the 90s, there was a huge Java boom, and Microsoft really was silent on this area. They observed everything, they watched everything, and then they stole everything that was really good and called it C#. So Microsoft paid really good attention, and they did notice where the virtual machine was slower because it had to run that process over and over again. So Microsoft created the CLR, the Common Language Runtime, which was their pseudo virtual machine. And what they did is when I write C# or I write Visual Basic or I write any other supported language within Microsoft's family and I compile it, it doesn't compile down to machine code. That's what all the other compilers used to do, like C and C++. It compiles down to MSIL, which is the Microsoft intermediary language. So what they do is they wrote a common language that all their languages can work with. So back in the day, in the early 2000s, Microsoft came out with this thing where Visual Basic programmers and C# programmers are gonna, hold hands, sing songs, and work together without any problems. Before that, back in the 90s, either you were a VB shop, you were a C# shop. I mean, you only wrote one language because the interoperability between languages was really, really difficult. And I couldn't just grab somebody else's code and start using it within my program. So this whole concept, I didn't really think was going to take off and work. And at the time, in the early 2000s, I was a Visual Basic programmer. That's actually where I spent a lot of my time in those years. And we hired on a C# guy, and he was like, I love C#, and eventually he did get me to drink the Kool-Aid and I switched over. But during that time, I really was concerned that we weren't going to be able to get share reusability and stuff like that. But Microsoft said, don't worry about it, you will. And what basically happened is he wrote his classes, he wrote his modules and DLLs and all that stuff. And when he compiled his work, it compiled down to MSIL. I did all mine in Visual Basic, I compiled it, it went down to MSIL. All of that just played together. So they created a low-level language. but not as low as like machine level. They created kind of a pseudo assembler style language, and you can actually decompile it, and I can take a .NET program and decompile it and view it what it would look like in C# or in Visual Basic. So I can actually toggle back and forth and see how they both look. So basically, that's what MSIL is. Now, what they did is they decided that they wanted to have more support, and they wanted to make it more efficient and more effective. So they actually took their common language runtime, the CLR, the .NET framework, and they created that JITting process that I talked about, which was just-in-time compilation, which actually sped up the entire process. So what would happen is you'd have the intermediary language, and somebody like double clicks on the exe and they're going to run it. It runs through the JIT compiler, and now it's down to the native language. So now it's down to the machine code, and that gets cached. So the way that Java would work is it would go all the way back to the beginning, do it again, go back to the beginning, do it again. So it always interrupt and have to go through this process of interpreting what's going on, where what they basically did was just cache the compiled code. And it's like, well, we compiled it already once. Let's just hold it here, and if they want to run it again or run a method again. That was the other thing they did, is they broke it down. So instead of compiling the entire program, the just in time means you are compiling the method that's being called. So if you're going to the login, just the login code is getting compiled and passed down to the CPU. After you log in, whatever that next event is, maybe get details, get client details, then that would get compiled and passed down to the CPU. But then it gets cached. So then if you ever go back to login, boom, it's already there. It doesn't have to, take as long. And if you get client details, it's already there. So that's kind of what they did. So now we're expanding. All right. So back in the early days of the .NET framework, so in the 2000s, mid 2000s, there was a group that was from Novell, and they were working on kind of a hobby project, and that became Mono, the Mono project. And what they wanted to do was they wanted to basically port the entire .NET framework over into Linux, because Microsoft, they had this great thing that they leveraged from Sun's experience, and they just didn't port it to anything other than Windows because they're Microsoft. I mean, they're getting better, but they're like, hey, this is our operating system, this is our language, this is what we care about, But Miguel and some other people were really, really aware that it could be so much more. I could write a program and I could run it anywhere because it's truly the same thing as Java, and there's nothing available in Linux. So they actually worked on rebuilding that whole .NET framework for Linux. And that's what's called Mono. So Mono existed, and that went really, really well. It actually went through a little bit of a rough, bumpy time with them and Microsoft, but actually today, Microsoft completely open sourced the common runtime language. So the framework is really in a different spot than it was, 10 years ago or even longer. So anyways, so the Mono project existed, and now you could start running .NET programs on Linux. So if you were a Linux person, if you used like Ubuntu or something like that, you could still, to this day, I do it all the time. I even do it on the Raspberry Pi. I'm running Linux on a Raspberry Pi. I just installed the .NET framework. It lets me write C#, and I can interact with that device. So they were doing that for quite some time. And then along came this whole mobile thing, the iPhone and the Android and the Windows Phone. There's, and really same problem. We've got all of this proliferation of devices, all of these different operating systems. There's no cross-platform. Nothing exists in this space. And Miguel, thought, let's see if we can build something that will be a .NET framework for the phone. So that's really where they went. So they created the Mono framework, and specifically Mono Touch was the iOS framework that would compile for the iPhone, and then they had Mono Droid, which was the Android version. Now, since then, it has evolved, and there's actually a whole backstory there. Novell got purchased by an investment company. They didn't realize what gold they were sitting on. They fired the whole team. They said, "What do we have guys here writing software for? We're a networking company. We're Novell. We're hardware and software." And so they let them all go, and then Miguel hooked up with Nat, and they ended up building Xamarin, which was a company that just dealt with the mobile space. They worked with Novell and said, either you're going to let us buy the work we did there, or we're just going to rewrite this because this work has to get done. They struck up a deal with Novell, and they were able to get the work that they were doing at Novell, and then they moved forward with Xamarin. So Xamarin's actually the company. Now, recently, within the last few months of me making this recording, Microsoft now purchased Xamarin, which totally makes sense. It should be there. So, I'm hoping in 3 months from now, the word Xamarin still exists, because that's what I refer to this as. But that's really the company that built this framework. Now, if I go back here, there is something a little bit different. So you have the JIT compiler that compiles just in time, and then every time you go in, it does, redoes this again. Now, once you get into the iPhone said, yeah, we don't have any interpolated compilation that is allowed on our phones. That's why the Flash player and different things, you can't get a Java app to run on the phone. So what Miguel did is he came up with ahead of time compilation, which, to be honest with you, is just a compiler. I mean, that's what we used to do with, C++ back in the day, but it's truly compiling it. AOT is what it's called. It's ahead of time compilation. And basically what they're doing is, instead of JITting it, they just take all of the code and compile it down to binary, ones and zeros. That's built for the specific processor that exists, the hardware that exists in the iPhone, the operating system, and it works specifically with the chipset. So all of that's done. So now when I compile something using the Xamarin.mobile and Xamarin.iOS and Xamarin.android, but when I compile using Xamarin, it actually gives me a binary that is exactly the same as if I were using the native tools. So, for example, if I'm going to build an iPhone app, it's Apple, all right? And Apple is just like Microsoft, just like everybody else. If you're going to build an iPhone app, you have to do it on a Mac, period. So the Mac is a requirement, and you used to have to do it in Xcode. So if you were building something, you'd either be using Objective-C or Swift or something like that. Since that point, Xamarin has done a lot of work to make a compiler that builds an application, and it has the same binary as if I were doing it in Xcode, and all of that's together now. So you still have to do it on a Mac. It's getting a little bit better. They're doing build servers, and some people are integrating it into Visual Studio. And now that Microsoft purchased Xamarin, I'm going to bet that we're going to see a lot more moving into Visual Studio. Right now I use Xamarin Studio. Works well for what I'm doing, but that's just something that happens. Okay, so we've got the Mono framework, which is the low-level framework that was used with Android. So it's just the whole framework of, dealing with strings, dealing with variables, dealing with all of that stuff. That's the same. But then they built the Mono Develop, which is now Xamarin Studio, and then Mono Touch, which is now Xamarin.iOS, and then now they've included the Xamarin Dot Droid. So, okay, so once we get here, we have to build apps and do stuff with it. There is an app developer program. It's not optional. If you want to get something onto your phone, you're going to have to use the Apple developer program. Later in the semester, I'll go through the details of how to actually push code to your phone. But for right now, there's really a couple of options you have okay, so you can be an Apple developer for free. All right, so you can just go to Apple, developer.apple.com, create an account. You can get videos, you can go through tutorials, you can get an SDK, documentation, all of that stuff for free. But if you want to like get an app on your phone, then you need to become subscribed into their Apple developer program. So as an individual, so I build apps on the side, and I have an individual license, so it's just $99 a year, and then that gives me the ability to build an app and put it out into the App Store and put it out onto my regular device. So you have the enterprise account, which does the same thing as the individual account, but that one has the ability to do something called ad hoc distribution, which means that, like, let's say I worked at KC and I'm dealing with salespeople, and I want to build an app so that way the salespeople can report all of their findings and all of their contacts and all that information, and then that'll bubble back to the mothership so the salespeople can be out in the field, and it just helps the organization run smoother. Now, somebody like my mother isn't going to download this app and install it on her iPhone. It would never be released out into the App Store. It's something that's industry specific or company specific. So at that point in time, they need to do the enterprise, and then they have their own distribution channel just for their employees. And then student, we had to work with the lawyers and get Apple to approve everything. And so Fox Valley Tech is a student Apple developer center, so that way students have the ability to publish certs, do things, create provisioning profiles, and you're going to learn all about that later on. But basically, you will be able to get code onto your phone. You won't be able to get it out into the App Store, but you will be able to get the code onto your phone. So the way the App Store works is you build an app, you can push it onto the App Store. There's also Google Play. So Google Play is $30, and actually with Google Android, you can just put the code right onto your phone. So it's different. There's no real complex process. Apple does have a complex process, and I'm going to walk through that in a later week more in detail. But Google's pretty straightforward. There's things I like about each, and there's things that I don't like about each. So there's no perfect scenario here. So they both do the same. They're going to keep 30% of all the profit, and you keep 70%. If you are going to do distribution, it's a good idea. I think if you're going to try to get a job in this field, you should do distribution. It's really good if you walk into a potential employer and say, hey, you can download my app here, take a look at it, let me know what you think. So it is a good idea. Now, the way this works is if you build an app and you put it into the App Store, Apple pays you as if you're like a musician. You get royalties. So they own the app. They manage all of that, and you just get a royalty deposited into your bank account. And the thing I like about that is I don't have to deal with sales tax. I don't have to deal with any of that. I just take it as additional income. Yay! And that makes life really, really easy for a developer, especially if you're doing this as a side job, as a hobby. On Google's side, Google Play, they don't do it that way. They still take the 30%, but what they do is you have to actually designate the state and the tax code. And once you start dealing with like European countries, you got the VAL, the value added tax, and stuff like that. So if somebody in Wisconsin buys my app, and because I'm located in Wisconsin, I need to pay like an additional 5% sales tax on that. So it's a little bit more muddy on that side. I don't necessarily like the way that Google does that. And the way that you get the code on the phone is a little bit different, and the way that you get code into the store is a little bit different. So the iPhone has a really complex process of creating digital keys and signatures, and you put in devices and it creates profiles. You have to install the profiles on your machine, you have to install the profiles on your phone, and then when you compile the code, you have to compile it using your encryption keys, so that way it's digitally signed. So within Apple, it is more complex to get your code onto the phone. And then you also have to pay them on top of that to get the code onto the phone. So the first time I went through that, I was like, you got to be kidding me. This is a lot of work and this seems really crazy. I came from a Windows development background, so for me, I would build an exe and pass it to my friends and life was good. Apple doesn't play that way. Google does. So Google, I can put my code, I create that APK, I can sideload it, not a big deal. I can put it out onto a website and install it. It works really easy. Getting it into Google Play, I upload the APK, put a couple images out there, put a description out there, hit apply, and it's in the store, within an hour. It has to replicate across all of the different stores, but it's there. It's really quick. It's really easy. Apple's not that way. So after I get everything working and tested, then I have to switch over to a release profile or a distribution profile and then compile it using that digital signature. And then I have to give it to Apple, which isn't even the easiest process, just giving them the app. And then once they have the app, then they actually look at it. So it may not hit the store for 2 weeks. So you have to kind of, when you're working with a customer, add that into your time frame because, it's tough because people will be like, well, I want a release date of January 1st. Well, I can't guarantee January 1st because it's up to Apple. And sometimes, many times, they'll reject it. They'll say this feature needs to be added, this feature needs to be removed. So they'll review it and they make sure that it complies to all of the requirements before it gets released into the store. So they're two different systems. There's things I like about each, there's things I dislike about each. There's no real perfect solution here. Security-wise, Apple definitely has the security focus. I think they've done a really knockout job. It's just a pain dealing with it. Android made it really, really easy. I can get stuff built, tested, out into distribution really, really quickly and easily. But security-wise, you can have people writing malware. You can tuck nasty things inside apps, and I don't like that. So there's really no win. But they're two different systems, and you got to know that. So they're just different. Okay, so underneath the hood, both of them have their own SDKs, their own, and all of that gets installed when you install Xamarin. It'll go through. That used to be really cumbersome. You'd have to install all this stuff separately. They've got a single installer now. Boom, it all goes. It's already been installed on all your virtual machines. If you're a Visual Studio guy, and I'm a Visual Studio guy, I spent many, many years in Visual Studio. You can, at this point now, compile and do things in Visual Studio. That's not the way I'm doing it. So if you follow along the way I'm doing it in class, that's fine. If you want to try to do it in Visual Studio, you do need a build server. If you can get your Mac that's running in VMware as your build server, more power to you. I wouldn't waste too much time on it. I do think you'd have to be on campus to get that to work. But if you want to not follow what I'm doing, I'm going to say that's okay. But it's going to be more work for you. But once you get it, then you'll be working in Visual Studio, and you can show me, and I'll say that's really cool because that is cool. But for right now, I'm going to be using Xamarin Studio. It's stable. I know it really well. It works really well. It's cross-platform. So anyways, underneath the hood, both iPhone and Android have specific ways they deal with different commonly used things. We've got media like audio, video, stuff like that, OpenGL for gamers. We've got different things like message boxes and UIKit. We also have core services like your address book, your SQLite. So that's all built into the iPhone. Now Android has the same thing as well. They've got their own SDK and they have their own core services and their own UI elements. Now the way this used to work going back, boy, a year and a half ago or so, you would develop all your user interface in Android, and then you develop your entire user interface in iOS or the iPhone, and then you'd have a shared library. And I'll go more into detail with this later. But what Xamarin realized is there was like a lot of work being done to support this, and just like the whole .NET framework, they thought we can streamline this. There's a lot of reuse of effort. So for example, just things like getting the address book. It's a core service. I can get the address book. There's specific code I need to write for the iPhone to get the address book contacts. All I want to do is get the contacts, a list of contacts. Why do I have to write it one way for the iPhone and write it one way for Android? What they did is they've abstracted it. They've written all of the code plumbing to get the addresses from the iPhone and Android. And now within Xamarin, and Xamarin Forms is the specific way I'm referencing, I can write it one way, and then it underneath the hood, if it's on the iPhone, will do it one way. If it's on the Android, it'll do the other way. So it gives me the ability to really write one code base, which is really, really nice. I know early on I wrote an app that used GPS, and I fought forever getting the GPS working. And then I had to fight forever to get the GPS working on Android. And then it was like a month later, Xamarin.Mobile came out, and it truly was like 2 lines of code. Because really all I want to do is like, hey, what's my current longitude and latitude? You know, it's really simple. That's all I want. So what they did is they wrote all of the plumbing work that gets that on each platform. So that way I write it once and then it just works. So it's more developer efficient, but it's also compiles down to the same native code. So it's not like there's a lot of bloat or overhead. We're dealing with ones and zeros. It's just being interpreted and built a little differently. So MonoTouch is open source. It is an open source project. Anybody can use it. Actually, everything's open source now. It used to be where Mono framework was open source, but the MonoTouch, which was the compiler, that was a premium offering. So I would actually pay, personally, about like $1,000 a year just for a license for getting things out, which kind of sucked. Microsoft bought them, and now Microsoft open sourced all of this. So it's good for you guys. It's good for everybody. So anyways, it's a good compiler, and that's going to be what we're going to be doing. So I just wanted to go over a little bit about how we got here, why we're doing what we're doing, and the benefits of it. So anyways, hopefully you found this helpful.